you're watching the video, we just went over the two definition ones. They're easy. Don't worry about it. I think Tiana's the only one not here. All right. So, 39. It's interesting. This is something, and so it's not you guys. It's every class I've had, and this must be one maybe of many things that I do a lousy job of explaining. But, quit nodding your head. So, whenever it says, and this is very common, we see it, find the equation of the tangent line. Ignore what they give you, ignore all that stuff. If it says find the equation of the tangent line, the first thing you should write down is this, right? I mean, that's what it is. Every time they say find the equation of the tangent line, they're just saying find an equation of a line. Any line. The equation of a line, point, slope, form. What do you need? Point and slope. I think they told you f prime of 1 is, but I'll admit, in some of these problems, like this one, when they ask you for the equation of the tangent line, all the other stuff they give you seems so confusing sometimes that it tends to cloud the issue. So you need to clear through that clutter and just say, what do they want? Oh, they want the equation of the tangent line. Oh, that's that. What do I need? I need a point and I need a slope at that same point. Well, they told me f prime of 1 is 4, so where does that go? That goes right there, right? That's the slope. And now I need the point. Well, I need the point at 1, so it's got to be a 1, right? That's the x value. And so what I need is f of 1. Now, I think it referred to example 5 in the book. So you go back to example 5. They have a graph of f. We look at the x value of 1, and it looks to me like it's roughly 5. It's between 4 and 8. I would say, yeah, look at the thing. So that's it, right there. And it's invariably when we do these, people go, oh, man, that was easy, right? I mean, because they really are. I mean, it's just, but there's a variety of ways that you'll find the slope or you'll find the point, right? It might be an equation, might be a graph, might be a table, might be all kinds of ways you'll have to get it. But in the end, that's all you're looking for is a point and a slope to plug into the equation. All right. I would like to do 46 and then move on to some other stuff unless there's some stuff really bugging you. If there's some other ones you want to check, again, I've got these solutions manuals, some of those shortcut ones you did, you're not quite sure if you did those right. Very important that we do those right, but we need to move on to a few things too. So I've got the resources for you to check those and see how you did. But I do want to talk about 46 because they say f of x, I think they called it f of x, and it's square root of x minus 3. Now I did have a few people come to me and look at this problem and they tried to do a conjugate. And good for you because you're paying attention to what we're talking about, right? And this does have the look of a conjugate kind of thing. Radical x minus 3, we could do radical x plus 3 to the top and bottom. Now it turns out it's not a good idea. Okay? But you know what? That's part of doing algebra. You gotta find the right thing, and sometimes you try something that doesn't work. Here's why it's not a good idea, and I'd rather use a better example. Let me use an example here. I'll use the idea of factoring and canceling. I've been talking about these 3 different algebra techniques we need to be able to do, but sometimes they don't do anything for us. And one was factoring and canceling. So if I give you a problem like this, okay, I would hope you would all go, wow, yeah, that's x plus 3, x minus 3. That's like that. And then that does that, and so we factor so we can cancel, right? They kind of go together. And so that's a great thing to do on that problem because it simplifies it. But if I gave you the problem x squared minus 9 over x minus 2, right? Well, then you factor it, but then you can't cancel anything. So in that case, I wouldn't factor. I would just, in that case, we would just leave it. There's nothing really we can do. Okay, so sometimes just because you can do something doesn't mean you should do something. All right, so that's kind of the case here. What we're trying to do is do the derivative. So we want it to look like a power rule. So we want like x to a power. So here's what I would suggest. You got one of 2 things to do. One of them I like better than the other. So the first one I'll show you is the one I don't like as much. So one thing we could do is we could take this top. I'm going to write that as 1/2. And then I can take the top there. Ooh. Okay, I can take the top part and move the x up as a -1 power. And then distribute. Okay, so that's fine. And when you distribute, you add the powers together. So half and -1 would be x to the -1/2, and then 3 times that would be 3x to the -1. Now we can do our derivative with our power. Okay? Now the one I like better, and we're going to see this a lot this year, is to split it apart. Put this over this, so that'd be x to the 1/2 over x, and then put 3 over x. And so then what you get, you subtract the power, so you get x to the -1/2, and then bring that x up is 3x to the -1, and you get the same thing. Now, we just see a lot of these, and I just think splitting it up. So what will happen is you'll see a problem like this. I say, I don't know what to do next. I'll say, well, split it apart. Split it apart. That will be my directions, and this is what I'm talking about. Split it apart. If you want to move it up and distribute, that's fine, but it just seems like, through my experience, it's been this split it apart thing works good. Now, you got to be careful with fractions. Let me do a quick example here. 3 plus 4 over 7. Well, we all know that's equal to what? 1. So if I split it apart, this is what we're talking about. Split it apart. That still equals 1, right? 3 sevenths plus 4 sevenths, 7 sevenths, that's 1. Okay, so that's good. So, good. Smiley face. Okay. Now, if you reverse that, right? Can you split it apart like that? That does not equal 1. That is bad. Okay? That is bad. All right? So when you split apart a denominator, you have to, in other words, don't split apart a denominator, right? You keep the denominator together. It goes under each of the pieces. You can split the numerator, okay, in its individual pieces. So that's the kind of problem we would want. So if this would have been flipped around like this, then there's really nothing we could have done with that. And we'll have to learn a new rule for how to handle that. And we will. Okay? Well, you could do a conjugate, but I don't think it would get you anywhere. You could do the conjugate to that, and then nothing would cancel or anything, and then it would actually be more complex than what you started with. But some people might do that. You might try it, and you say, oh, no, that didn't get me anywhere. So you go back to where you started. You'll see as we go through this year, there are going to be problems where you've got several paths you go down. Sometimes you go down the wrong path. You get to a certain point, you say, this was a bad idea. You turn around, come back, and then you go down a different one, right? I mean, that may happen. Okay? All right. Let's take a look. Go ahead and get your notes out at this point. Oh, and while you're doing that, I am going to make one other comment here. So as you're getting ready for this, I'm just going to, I'll write something up here. So, and we'll talk about it just quickly. You don't need to write it down or anything. All right, so the top function there, what's the derivative of that? 3x squared. Derivative of 7 is 0. A constant, the derivative is always 0. Okay, and this bottom one, derivative is? Okay, let's talk about that for a second. So what we're saying is, we've got two f functions that have the same f prime. Remember when I gave you an f prime graph, told you to draw the f? So I gave you an f prime graph, said draw the f. And so as we started to draw the f, I would say, well, where do you start it? And you would say, what? Doesn't matter, right? Because if you shift a graph up and down, the slopes don't switch. They're in the same places. They're just moved up and down, but the slopes are all the same. Well, this shows that, right? Isn't this the same idea, except instead of graphically, just symbolically? You've got two f primes that are the same, but their f graphs are just vertical shifts of one another. The top one is up 7, the bottom one's down 8, okay? And so this shows the same thing. So we can see why one f prime could have several f graphs that it goes with, okay? And part of it is because of that constant there. When you do the derivative, it's just 0, and it goes away, okay? So it's kind of a nice connection to some stuff we were doing earlier. All right, this is what I want to talk about today, this LIM thing, right? The limit, the limit. So as we see this notation right here, this reads the limit of f of x as x approaches a is equal to some number L. Okay? The limit of f of x as x approaches a is equal to some number L. Now it's possible that there is no limit. It's possible that the limit does not exist. Now there's a little bit of language there that is important to understand. We talk about functions are undefined. If you plug in a number and don't get out an answer, we say the function is undefined. With limits, if there is no answer, we say the limit does not exist. Kind of a subtle thing, but it's really not proper to say a limit is undefined. Okay? A function can be undefined, have a value or not have a value. So it has a value or it's undefined. A limit has a value or it does not exist. Okay? So just similar things, but yet just slightly different ideas. Okay, now in everyday language, what this means, and you can just add this right onto that, is it means what are the outputs getting close to? We're talking about the y values now. So when we talk about a limit, we're talking about the y value. Okay? It's what are the outputs getting close to as the inputs get close to a. All right? So you can write that down underneath there if you want as kind of a, a more everyday kind of meaning. Right? Now notice the word close in there, because it doesn't matter that you can actually plug a 0 in for h. For example, in those limits we were doing, we wanted to plug a 0 in for h, and in the beginning we would plug a 0 in for h and we couldn't get an answer. But then we did some algebra magic to it, and then we could plug a 0 in for h. Okay? It doesn't matter what happened. I mean, because the question has come up, why this LIM, why this limit notation, h gets close to 0, why can't you just say put a 0 in for h? Because that's not what limit's about. Limit's not about what happens when h is 0. Limits are about what the y values are as h gets close to 0. Now that seems like kind of the same thing, and many times it is the same thing. You put a 0 in for h, what you get is what the outputs are getting close to. But there are some subtle differences, and so that's what we want to focus in on today. All right? So it's this idea of getting close to. Now, I use this example. My high school teacher used to say this. Think of a limit this way. If when the bell rang and we were going to leave the room, I told you to get up from your desk and go halfway to the door. And then I said from there, go halfway. And then from there, go halfway. And then from there, go halfway. Could you ever get out the door? No. And so that's, then of course he would say, so without limits, you would be stuck in here forever. Okay, but we have limits so you can leave. But the idea is that even though technically if you kept doing that and kept doing that and kept doing that, you would never get to the door. The idea of a limit lets you get to the door. In other words, the limit is where you're getting closer and closer and closer to. If you keep doing that, you're getting closer and closer and closer to the door. But you have to do it for infinity, and we know you can't ever get to infinity, right? And so you would keep getting closer, keep getting closer, keep getting closer, but the limit is the door. That's the thing you're getting closer and closer and closer and closer to. Okay? So that's one way to maybe try to conceptualize a limit. All right? So we're going to look at a little video here. You don't need to write this down necessarily right now. Okay? But I want to prep this video a little bit, so you're going to see some of this in the video. So I want you to kind of get this idea a little bit ahead of time. So what I've done is just given you this limit here. Now this doesn't look anything like our definition of the derivative. Now keep this in mind. The definition of the derivative, f of x plus h minus f of x, limit as h goes to 0, that is a special kind of a limit that means derivative. It lets the 2 points get really close together. But limits, like I said, Mrs. Payne can teach a whole section on limits in advanced math. You wouldn't need to know anything about derivatives. So here's one right here. Okay, this doesn't have anything to do about 2 points or any of that kind of stuff, right? This is just saying, what are these outputs getting close to as the inputs get close to 2? What would you say to that question? 5. As x gets close to 2, right, as we're coming in here, as x is getting close to 2, the y values are getting closer and closer and closer to 5. They say, well, why don't you just plug in a 2? Well, yes, in this particular problem, that's what you would do. You plug in a 2, 2 squared is 4, 4 plus 1 is 5, that's your output. The limit is 5. That would be the answer. Very easy. That's the easiest, simplest kind of limit there is to do. All right? Now, we're going to do some limits like this. Today, you'll have some of these to do. Now, I've added a graph here, but a lot of these we'll do without a calculator. But I want you to be able to visualize that there's something going on graphically here as well. Because we're talking about y values and x values, so we want to be thinking about the graphs. If you were to graph this on your calculator, this is what you would get. It would be a line. Now, you wouldn't see on your graphing calculator a hole. But if you traced at 3, there would be no value. Because what happens when you put in a 3? You get 0 divided by 0. Now, that's undefined. Now, I might just make a little side comment here. 0 over 0 is different than getting 3 over 0, or 6 over 0, or 7 over 0, or something like that. Those are different. They're all undefined. But 0 over 0 is a special kind of undefined. It's got a name, which we'll talk about later. But for right now, just think, if I get 0 over 0, I got to keep going. There's more work to do. If I get 6 over 0, 7 over 0, 3 over 0, something like that, limit doesn't exist. We'll just stop at this point. Now, later we'll investigate more. But for right now, limit doesn't exist. It's undefined. Okay, those values are undefined. All right, so we get 0 over 0, so that tells us we got to keep going. So, looking at the graph, what would you say the limit is? Well, now listen, you got to go back to this. When I say what is the limit, you should be thinking, what are the outputs getting close to? What are the y values getting close to as the inputs get close to 3? 6. The limit here is 6. Okay? This right here is what limit is. This sentence right here is what you've got to understand. Limit is what the outputs are getting close to as the inputs get close to A. So on this graph, as the inputs get close to 3, the y values are getting closer and closer and closer to 6. But you say, but they don't equal 6. There's a hole there. That doesn't matter. That's what I'm talking about. It doesn't matter what happens when x is 3. It matters what the outputs are getting close to when x gets close to 3. So the answer to this is 6. Now, how will we work this? We'll work this just like we've been working our definition problem. We'll work some magic on it. Algebra magic. What will you do? You'll factor it. One of the 3 algebra things I'm telling you have to be able to do. One is factor and cancel. One is common denominator. One is conjugate method. Okay? So we'll go ahead and factor. We'll cancel out an x minus 3. And guess what we can do now? Now we can plug a 3 in for x. You see how this is like when we plug a 0 in for h? We tried to plug a 0 in for h. In our problems, we get 0 divided by 0. So we did some algebra to them, got to a certain point where the h is canceled. That allowed us to then put a 0 in for h. We're doing the same thing right here. We went ahead and factored. We canceled the x minus 3. That's what was causing us to get our 0 on the bottom. But now it's gone, just like the h disappeared. So now we can plug in our 3. 3 plus 3 is 6. That's how we know the limit is 6. So on the problems you're going to be working, you won't have this picture in front of you because there are going to be no calculator problems. So you're going to do this algebra and you're going to get 6. But I want you to have in your head a visual picture of what you just found. What you just found is this function. I don't know. Let's pretend we don't know what the graph looks like. This has some graph. And as x is getting closer to 3, the y values are getting closer and closer to 6. That's what a limit is. That's what that one happens to look like. All right. So we're going to watch a little video here. All right, now this is a website that if you go onto our page, wow, I didn't realize this was so far away. Okay, never mind. If we go to our home page and you go down here to the web links, and under the web links right here it says videos about continuity and limits. If you click on that, it will take you to this page right here, calculushelp.com. And there's some video tutorials here, and we're going to watch a few of these right here. They're kind of good, and they do a pretty good job of explaining this.
You may have heard a lot of talk about limits, but the plain fact remains, most people don't understand what a limit is. So for now, we're going to focus on what is a limit. In basic terms, a limit is a height that a function intends to reach. That's pretty important, so let's say it one more time. A limit is the intended height of a function. Now this might give you pause. You might think, how am I supposed to know what height a function intends to reach? I don't even know what my intentions are most of the time. How am I supposed to discern the intentions of a function? That's a good question. And the fact that you don't understand exactly what I'm talking about is because all of the functions you've been dealing with, or at least most of them, have had their intentions completely clear. If a function intends to reach 3, it reaches 3. If a function intends to go 6 units high, it goes 6 units high. There hasn't been a lot of mystery so far. So I understand that you might be a little confused, but you've dealt with function heights a lot, so we might as well review function heights a little bit and then get into exactly what I mean by intending to go to a certain height.
Okay, so I like the language they use there. It fits in with what I was talking about. I used the word approach, but what are the y values getting close to? What are they approaching as x approaches this? And they said the intended height of the function, right? It's kind of like that line we saw. You could tell that the line was intending to hit 6 when x was 3. It just didn't because it was undefined at that point, but it doesn't matter. It's not the height of the function that matters, it's the intended height of the function. It's what they're approaching. So it's another way to think about it.
Let's start by looking at a very simple function graph. What I have here is the function f of x equals x squared, basic parabola. You'll notice that the function changes heights all throughout its domain. That's a very fancy way of saying that the function reaches many different heights based on whatever the x value you're looking at happens to be. For example, what if I look at the function height that corresponds to x equals 2? Well, it's not very difficult to figure out exactly how high that function is going to be when x equals 2, because all I have to do is plug in that x value into the function to figure out what that height will be. So, if I plug 2 into x squared, I get 2 squared, or 4. This means that the function reaches a height of 4 whenever x equals 2. Pretty simple. But now I can create my first very basic limit statement, and that is the limit as x approaches 2 of f of x equals 4. This just means that whenever I'm getting very close to the x value of 2, my function is getting very close to the height of 4. There's nothing really earth-shattering about what we just learned. But that changes when we examine functions that do not reach the heights they intend. Take, for example, this function. G of x equals the fraction x squared minus 6x plus 8 divided by the quantity x minus 2. Here's what the graph looks like. It looks like a plain old line. Or does it? If we zoom in, you'll see that it has a hole in it at the coordinates 2, negative 2. The hole exists because plugging x equals 2 into the function results in 0 divided by 0. And we know that dividing by 0 is a very bad idea. It breaks mathematical laws that we really can't even get into here. However, though this graph has a hole in it, it still possesses a limit when x equals 2. Clearly, the graph intends to reach a height of negative 2 when x equals 2. Even though that graph doesn't actually reach that height, it doesn't matter. The limit still exists, and we can say that the limit as x approaches 2 of g of x is equal to negative 2. This begs the question, when exactly does the limit exist? We examine that in the next module. Now you have some idea of what a limit is, and we need to talk about when does a limit exist. To illustrate my point before we get started, let's set up an example. Let's say you and a friend are going to meet for dinner, and you're meeting at a diner that's centrally located between the two of you. If you live east of the diner and your friend lives west of the diner and you both want to drive to meet there, ideally, the roads which lead to the diner will lead you to the same place. If you travel towards the diner from the right, or east, and they travel towards the diner from the left, you should meet up in the same place. Mathematically, this is basically what a limit is. A limit exists if you travel along a function from the left side and from the right side toward some specific value of x, as long as that function meets in the middle, as long as you arrive at the diner, as long as the heights from the right and the left are the same, then the limit exists.
Okay, that is a really important visual, what you just saw right there. That is something that I really, especially when you're looking at graphs. We're going to have some problems today where we're going to do some algebra to them, like the ones we did here a little bit ago, and they're going to do some examples again. And graphically, where we're going to look at some graphs and have to do the limit. And I want you to think of those arrows right there. Think of the cars. And many times you'll say, well, you'll ask me, well, what's the limit at this one? I say, well, do the cars meet? Or does the limit exist? Well, do the cars meet? Right? I will say I like to refer to this limit because I think it's a great way to think about it. You think about the cars and they have to come from both sides. And do they meet? If they meet, the place they meet, the y value they meet, that is the limit. Okay? And if they don't meet, then the limit doesn't exist. And so that visual there with those arrows coming in or with the cars coming in is a great way to think about it.
Now it's time to get down to the brass tacks and look at this mathematically. Take a look at the graph of this function f of x. Visually, you can see
what kind of function is that?
At x equals 4.
Piecewise,
So,
right? Piecewise is
if we
going to
travel
present some
towards
challenges.
4 from the right, we will arrive at a height of 2. However, if you travel towards 4 from the left, you will arrive at a height of 1. This means that no limit exists for f at x equals 4. Let's go back to our diner metaphor for just a second. Notice that as I'm traveling along the road from the right, I end up at a height of 2. But if you travel along the road from the left, you end up at a height of 1. These heights don't match. We won't both arrive at the diner, and no limit exists. We call the height at which we arrive from the right the right.
Notice this
limit
notation
of f of
here.
x, as x approaches 4 from the right. And we denote this with a little plus sign in our limit symbol. Our height that we arrive at from the left is called the left-hand limit of f of x as x approaches 4, and it is denoted with a little negative symbol. Mathematically, in order for a limit to exist, both the right and the left-hand limits must be equal.
Okay, so this would be a common question as well, or directions for you. Maybe we have a graph like that one, and I'll say, find the limit at these places, and then I'll give you some limit problems to find the limit. And then I will say, if the limit does not exist, discuss the one-sided limits. The one-sided limits means from the left and from the right. So a normal limit has to come from both sides. So the limit as x approaches 4, the cars have to come in from both sides and they have to meet. If they don't meet, the limit doesn't exist. So if the limit doesn't exist, I might say discuss the one-sided limits, and this is what you would write. Well, the limit from the right, this little plus sign means from the right, on that example was 2. The limit from the left was 1. They're not equal. The one-sided limits will always exist. The car on the left is always going to go somewhere. The car on the right is always going to go somewhere. But if they don't meet, then the limit at 4 does not exist. Okay? Yeah.
So does that mean the only time there isn't a limit is piecewise?
That's a big part of when it doesn't exist, when there's some sort of break. Now, there are some other graphs that have breaks in them. For example, think of the tangent graph. Tangent graph goes up here, and then it's down over here, and so the cars wouldn't meet, right? So it wouldn't have to be a piecewise. You can have other kinds of functions that have breaks or gaps or something in them, but a big time is piecewise and those kind of things. Okay? All right. So, but that's another one. Now, we'll get into in a later chapter the vertical asymptote ones, but that's another big one is vertical asymptotes. Breaks like piecewise or vertical asymptote type situations are big ones.
Now let's change this function just a little bit. This new function, we'll call g of x, does possess a limit. Can you see why that's the case? It's because the function no longer has a break at 4. Now, there's something to be said here. The previous function did not have a limit at 4. It did have a limit at many other points. For example, a limit existed at 1, at 2, at 5, at 0. All these x values showed locations where the graph did not break. In essence, a graph will not possess a limit if it breaks at the given x value. That's why our new function does possess a limit at x equals 4. Now, let's go back to our diner example one last time. Let's say we're traveling towards the diner. We both arrive at the same location, but the diner isn't there. Maybe it's caught fire or something. Does that mean the limit doesn't exist? The truth is, the limit will exist even if the diner's not there, because you still arrived at the same place. In other words, mathematically, a limit can still exist if your destination is a hole in the graph, because it doesn't matter whether or not the point is actually there. What matters is that you arrived at that point, coming from the right side and the left side. In conclusion, a limit exists on a graph if you arrive at the same height coming from both the right and the left side of the given x value.
Okay, so we think about that now. We talked about the hole. That's why so many of the limit problems we do are hole in the graph problems, which is when you get 0 over 0. That's what is happening. There's a hole in the graph. Because if there's no hole in the graph, then it's just easy. You just plug in a value. You just plug it in and you get your value. And if it's a piecewise function, then you look at it graphically, mostly. It's what's going on, or else you have to graph it, that kind of thing. A lot of types of graphs have holes in the graph, like what we've been seeing. We have to do some algebra to them. And so they're going to quickly run through a little bit of algebra stuff. We won't watch the whole thing here because we've done some of this, but we'll look at this now. It sounds kind of weird on this one.
The next logical step is to try to figure out what the exact limit is. So that's what we'll be focusing on in this section. How do you find a limit? The fancy word for finding the value of a limit is evaluate. So when you see the directions evaluate, basically you should be expecting to get a numerical answer. There are three major ways to evaluate a limit. They are substitution,
Common denominator they left
and the
off.
conjugate method.
So we'll have 4.
We're going to go ahead and start with the easiest one, which is direct substitution. It is just as easy as it sounds. We'll take an example. Here's one. The limit as x approaches 0 of the fraction x squared minus 1 divided by the quantity 2x plus 3. In order to evaluate this limit, all you've got to do is plug in 0 everywhere you see an x.
Always the first thing you should do.
So we'll put in
Always
0
the first thing
everywhere,
you should do is plug it in and see what happens.
and we end up getting negative 1 divided by 3.
And you're done.
So our limit is negative 1/3. It's as easy as that.
Okay, so what that means is this would have some picture, some graph, and there would be no hole, nothing weird going on. At 0, it would cross at the point negative 1/3. That's the limit. That's what's happening. So always direct substitution is the first thing you do.
Unfortunately, not all limits are this easy. And you've already seen one for which that's the case. Remember that function that we were dealing with in the first section of this chapter? In case you don't, here it is again. A limit as x approaches 2 of the fraction x squared minus 6x plus 8, all divided by the quantity x minus 2. We looked at this before. It had a hole in it at the coordinate 2 comma negative 2. And we concluded from that that the intended height was negative 2, making it the limit. However, it would be nice to be able to figure out why this is true mathematically. And to do that, we'll have to use the factoring method. As you can see, and as we saw before, direct substitution results in 0 divided by 0, which is not allowed. So we'll have to resort to this new method.
Remember, when you get 0 over 0, it means keep going. Do some of the algebra to it.
If we factor it, we'll get x minus 4 times x minus 2. Can you see why that's a good idea? Well, the reason is because now the numerator and the denominator both contain the term x minus 2, which I'm going to cancel out. This leaves the limit as x approaches 2 of x minus 4. This is much simpler to solve because now you can use substitution. And when I do, I get 2 minus 4, which is equal to negative 2. Remember, we knew the limit was going to be negative 2, and we're right. Feels good to be right.
Okay, so I'm going to stop right there. They just go through another one that's the conjugate method, which is similar to ones we've done. And then they just talk about, evaluating those limits. So let's recap what it is that we saw there. And then I'm also going to kind of help you get started with the homework here on this. Okay, so So basically it comes down to this. When you're working a limit problem, one of three things is going to happen. So you're going to do your substitution. You always start with substitution. Okay? Now when you plug in for substitution, one of three things is going to happen. You'll get a number. Then you're done. All right? Like the example they did. You know, they plugged in a, I can't remember what that first one was. They plugged in a 2 and they got a 4 and that was their answer. They got a negative 1/3, I guess, wasn't it? They plugged in a 0. They plugged in a 0 and they got negative 1/3 and they were done. That was their limit. Okay? The second thing that could happen is you get 0 divided by 0. If you get 0 divided by 0, that basically means keep going. Okay? Keep going. That's do the algebra. That's when you're going to get into the factoring, the common denominator, the conjugate method, something like that. 0 over 0 pretty much means there's a hole in the graph. And as we've seen, when you have a hole in the graph, typically there is some limit. When there's a hole in the graph, there is some limit because the cars would meet, even though the diner burned down, right? That's basically what they said a hole in the graph was like. The diner burned down. The cars still meet there. That is still the limit. Okay? If you get 7 over 0 or something similar, some other non-zero number over 0, okay, 1 over 0, 2 over 0, whatever, then we say the limit does not exist. Now, later, we'll learn more about does not exist and we'll give some other reasons. We'll investigate it further. Now, also, though, be ready to discuss the one-sided limits. Now, that would be more on graph-type problems than algebra-type problems. But if you say the limit does not exist, be prepared to say, well, from the left it would be this, and from the right it would be this, and they're different, and that's why the limit doesn't exist. Now, in an algebra-type problem where you're not looking at a graph, it's a little harder to do, okay? So it may just, so if the directions don't say that, they just say evaluate the limit, then you might just say does not exist, okay? So those would be your three possibilities of what could happen. Of course, then somebody usually asks, well, what if you get 0 over 7? What's 0 over 7? That's 0. That's a number, right? So that actually fits this one up here. 0 over 7 is just 0. So your limit is 0. Okay, that means the graph meets right at the x-axis. Its y value is 0. So that's just an answer. Okay, just like some other number. All right. So what if you have a picture like this? Obviously, this is a piecewise, a kind of a crazy piecewise function with all kinds of things going on. All right, so this is going to be part of your homework. There's going to be a series of problems, and they're going to ask you just a whole bunch of limit things. Now, the homework today, there's hardly anything in there about derivatives or anything like this. It's kind of a little bit of a side trick. We're just over here talking about limits. What are limits, okay? But so let's say this is some function f, okay? Let's say they call this some function f. So if I ask you what's the limit as x approaches 2? What? Well, okay, back up. Let me ask, this is what I asked the other class first. This dot right here, okay? Let's talk about that. So what if the question was this? So here's the function f. I ask you, what is f of 2? Or f of 2 equals question mark. What would you say? Negative 1. That's what that dot is. That's the function output at 2. So f of 2, you would answer is negative 1. That's right. Now, if I ask you what's the limit as x approaches 2, you would say 1. Because that is where the cars meet. That is the y value where the function intends to reach. The limit is 1. The output is not necessarily the same as the limit. Now, so we talked about ones that had holes in the graph. We've never seen one here that had a hole, but then it had another value. That'd be like if the diner burned down and they rebuilt it somewhere else. You know what I mean? What do you mean? How does that work? With the function? Yeah. How would that be written, you mean? Yeah. It would be like this. You would have, who knows what that particular picture is, but you might say sine, f of x equals sine, I don't know what that is, whatever. We'll just make something up. And then you might say from 1 to 2. And then you would say equals negative 1, and I would probably put x equals 2, like that. Or you could just say,
Okay, so it's
for 2. It's just a value. Yeah, it just is it's not an equation, it's just a value at that point. Yeah, that's what it would look like in your piecewise function. Okay? Yeah, this would be a mess of a thing, right? You'd have this line from here to here, the line from here to here, you'd have a point there. But that's what it would look like. So it'd be this big, messy piecewise function. So what if I said, what is the limit as x approaches 1? The limit as x approaches 1.
Would you have to do the left and the right?
Think of the cars.
Do you want them separately?
No. I didn't ask for them separately, right? All I said was, what is the limit as x approaches 1? Does not exist. And again, remember when I said I want you to have this visual of those arrows coming together? The cars meeting. When I ask what is a limit, you want to think about the cars meeting. When you have a graph. Now, when you have an equation, we do the factoring, the canceling, that kind of stuff. But when you have a graph, picture the cars. So at 1, this car's up here, this car's down here, they don't meet. Limit does not exist. Now, then I would probably follow that up with discuss the one-sided limits. What's the limit as x approaches 1 from the right? 0. The car on the right is coming down here to a y value 0. From the left? 2. The car on the left is approaching a y value 2. It's actually not even approaching, it actually is 2, but that's okay. That's what it is, it's 2. Okay, so the car on the left, the limit is 2. Car on the right, the limit is 0. Those aren't the same, so we say the limit does not exist. The cars don't meet. If the cars don't meet, the limit does not exist. Where else here does a limit not exist? At 1 and at -1. Now, the ones at the ends, I wouldn't ask you on a graph like this, I wouldn't say what's the limit as x approaches 4, because we can't see on the other side of 4. There's no car coming in on the right side, so I wouldn't even ask that. I might just ask you from the left at the end there, right? The limit as x, well anyway, so you're going to get some of these kinds of questions with this particular picture, this kind of piecewise function. So once you get the hang of it, they're really quite easy. And there's not much work to do. You just write it down, the answer is done. So that part is pretty easy to do. All right, so on your homework sheet, it talks about some book problems. And then below that, it mentions this worksheet. And so we're going to do both of those things. Now, the book problems, like I said, don't take very long. And it does mention on that assignment sheet, it says something about 1 through 3 and number 7, doing those in class with a question mark. We're not going to do those right now, so you can skip those. Okay, so the 1 through 3 and the 7 with the question mark, just skip those for right now. Okay, and so this worksheet, this would be not using your calculator, this would be doing the algebra. So this is where I was talking about earlier. You start on this worksheet, you start by doing direct substitution. If you get a number, that's your answer. If you get 0 over 0, you keep going. Do some algebra. If you notice here, there's some radicals on here, so there's your conjugate method. If you look at number 7, that's going to be common denominators. The rest of them are probably some sort of factoring or canceling or something like that. And if you get 6 over 0 or 7 over 0 or something like that, then you can say the limit does not exist. The book problems will be more graphical probably in nature. They all involve something to do with limits.